In this week we will be talking about causal inference. And before we delve into the details of causal inference, it's important to make a distinction between statistical inference and causal inference, just so we know exactly what we're talking about. Statistical inference, which you usually do through statistical tests like the t-test or the f-test, refers to establishing whether a particular correlation or a particular effect that you observe in the data, whether we can also infer that this is likely to exist in the population. We do this either by assuming in a frequentist paradigm that it does not exist in the population, and look at the sampling distribution that would result from testing on a sample if it does indeed not exist in the population, and then see how likely it is to find the results that we do. If it's very unlikely, then we reject the null hypothesis. In Bayesian inference, we have a particular prior belief about it existing in the population, and we try to determine, based on the evidence and the data, the strength of the effect, the clarity of the effect, the size of the sample, and so forth, how much we should update our belief about the population. But in both cases, we see a particular effect in a sample, and we're trying to infer to what extent this could apply to the population. In causal inference, on the other hand, we try to establish whether this relationship that we observe might be a causal relationship. Now, this is partly just purely theoretical. We cannot statistically establish a causal relationship. But we do have certain requirements and certain concerns that would hamper this causal inference, so there is a lot of econometric modeling decisions that do relate to this requirement of a causal rather than a statistical inference. So the problem arises that when we see a correlation between two variables, there might be many causal patterns underlying this correlation. So one causal pattern, of course, is that X indeed is the cause of Y, which is often the reason why we look at the correlation. So we have some dependent variable Y, we have some independent variable X, we find a correlation, and we think that this correlation comes about because X might be the cause of Y. But there are many other possible patterns at play. So here's an overview of many of those possible patterns. In the top left we have X causing Y, which you might be assuming. But perhaps it's the second one on the left, which is Y causing X. If Y is the cause of X, we would see the same kind of correlation in our statistical data that we would see if X would cause Y. Or maybe the X does cause Y, but it does cause it through some kind of mechanism that might be captured by a variable Z. So X causing Y is just not the whole story. It's not necessarily wrong, but it's not the whole story. Or we might be in the top right, where X partly causes Y, but partly causes some intermediate variable Z that then itself has an effect on Y. Or perhaps X and Y cause each other, and there's a complicated endogenous relationship. Right? You can think of democracy and development, for example, where we know that more developed countries are more likely to democratize, but we also know that more democratic countries tend to have higher levels of development. Or perhaps, and this is the most important one that we will talk about for the rest of this lecture basically, there might be a relationship that X causes Y, but there is some third factor that impacts on both, either negatively or positively, but that has an impact on both the independent and the dependent variable. This, we will explain later, is what we call a confounding factor, and when there are confounders, then we need to be really wary with our causal inference. So here's an example where X causes Y, but Y also causes X. And so where we get a problem if we think that association or correlation is the same thing as causation. So imagine you prescribe a drug to a set of patients, some more ill and some healthier. And you want to see whether the drug works. And imagine that the ill ones are so ill that they also do not have the energy or the motivation to participate. They are too sick, they are not participating. And the ones who are healthy are more active and they want to improve further and they take the medicine. If you now look at a correlation between medicine usage and recovery, you will see that there's a strong effect, even though maybe the medicine wasn't working at all. It is just because the healthier people were taking the drug and the less healthy ones were not. A much more likely scenario, of course, is the opposite, where the healthier patients might feel sufficiently recovered and they maybe don't want the side effects of the drugs and they might decide to stop using the drugs, whereas the sicker patients maybe do take the drugs. And then you will measure the correlation and you find that people that take the drugs are sicker than those that do not take the drugs. And you might conclude that there is a negative or no association between drugs and recovery. In either case, we have a problem establishing the true relationship between the drug usage and health status, or basically the effectiveness of the drug. So we cannot simply say that correlation is causation. There can be other factors at play, or there can be an endogenous back and forth relationship at play. So let's look at a second example. Imagine you do a study among college students, and you try to establish whether they use or do not use marijuana. Maybe you use a sort of a questionnaire or something, and you establish what their GPA is. And you find that there is indeed a negative relationship. People using marijuana have lower grades. But it will be difficult to now fully establish what the relationship is, right? So we might assume that marijuana usage leads to lower grades, right? So this is probably the first most obvious conclusion. Those students who use marijuana are affecting their brains, affecting their levels of concentration, are maybe feeling a little bit too relaxed about the test and don't prepare sufficiently. They end up with lower GPA. But perhaps the opposite is at work, right? So we could imagine students who have a decline in their GPA to get stressed and disillusioned about this and lose motivation, and end up trying to relax by using marijuana. So we would have the opposite effect. We might have students with lower grades more likely to take marijuana, and the causal direction of the arrow will be in the opposite direction. Correlation is the same. Statistically, there's no difference here, but the causal direction is completely the inverse. Or perhaps there are exogenous factors, outside factors that cause stress. Maybe there are difficult relationship problems or problems with the family. And these additional stress factors might impact both on the likelihood to use marijuana, but might also impact on grades in a way completely independent of the marijuana usage. So if there's external factors that make one more likely to take marijuana and more likely to get lower grades, then we would observe a correlation between marijuana usage and grades that has nothing to do with the impact of marijuana on these grades. And finally, there's of course the possibility that it is just all randomly by chance. But here one would say that statistical inference should address this, right? So if we find a correlation, statistical inference is about establishing whether this is purely by chance or not. And if we find through statistical inference that it is not purely by chance, then there has to be some kind of relationship. But that the relationship can be from X to Y or from Y to X, or because of some third factors, or even more complicated causal patterns. And to explain this, we're going to change notation a little bit and make a few simplifying assumptions, just because it's easier to outline. So first of all, I'm going to use the language that is common in causal inference, which is not to talk about X and Y, but to talk about T and Y. Y being the outcome variable and T being the treatment. So think of the medical example where some patients get the drugs and others don't get the drug, and we want to see whether they differ. And secondly, just for simplification, we're going to assume that there is only two possible treatments, 1 and 0. You either get a drug or you do not get a drug. Or in a political context, you either see a particular advertisement or you do not see it. But the theory applies for scale variable causes, of course. It just all the math becomes more complicated and everything a bit harder to explain. So we leave that out of this explanation. So for the next few slides, we will look at one particular example, which is imagine the two groups of people, some with a college degree and some without a college degree. So those with a college degree, T equals 1, and those without a college degree, T equals 0. And then let's think about their future salary. Now, what we really want to know is whether the salary is increased or higher on average because some participants have a college degree or not. And so what we really want to know is what would the salary have been for somebody with a college degree had this person not had a college degree, and what is their salary now, and then look at the difference. And similarly, for those without a college degree, we would like to know what their salary would have been had they had a college degree, and then compare that to the salary they have now. And of course, the fundamental problem here is that we only observe one of those two states. For those with a college degree, we only observe their salary with a college degree and not without. And for those without a college degree, we only observe their salary without a college degree and not that with a college degree. And that means that what we really want to know, this causal effect at an individual level for each individual respondent, how much more would they have earned had they had a college degree, or had they not, how much less if they hadn't had a college degree. We can't observe and we can't calculate that difference. So here's an imaginary ideal table that we would like to make. We have a list of a set of respondents, we have their salary without the degree, we have their salary with the degree, and we calculate the difference. And maybe we want to calculate the average across the whole population by taking the average of that last column. And so we can see what the impact is of having a college degree on one's salary. Unfortunately, in practice we have this. We have all the missing data, because for those without a college degree we don't know what their salary would have been with a college degree, and for those with a college degree we don't know what their salary would have been without a college degree. And so we also can't calculate these differences, and we can't calculate the average. So even though we cannot observe the salary with a college degree for those without a college degree and vice versa, we can mathematically talk about this salary. So we can imagine it and we can give it a symbol and we can then work out the equations. So that's what we do here. So when we talk about the potential outcomes approach to causal inference, we're going to talk about the potential outcome of a salary of a particular individual given a college degree, and the potential outcome in terms of the average salary of that same individual without a college degree. Even though only one of those potential outcomes is realized, because this person either has or doesn't have a college degree. But we can talk about those two. And so we can talk about y1i, which means for the ith respondent, the outcome of y if the treatment is 1. Or y0i, and this is the outcome of the dependent variable for the ith individual when the treatment is 0. And one of those two is observed and one of those two is not. But mathematically we can talk about both. And then we can define the causal effect of the treatment on y as the difference between y1i and y0i. Yeah, so the difference in those two potential outcomes for a particular individual, depending on the treatment being 1 or 0, that is the treatment effect, the causal effect. And then we tend to take one step further, which is to, instead of talking about the treatment effect or the causal effect for an individual, we talk about the average treatment effect, which is the expected value of y given a treatment minus the expected value of y without the treatment. Yeah, so it's the, on average, in this case, the difference in salaries between those two potential outcomes across the sample or population. Yeah, so the expected value talks about the probability distribution of y given t, and looks at the differences between t being 1 and t being 0. So when we talk about the average treatment effect as being the difference between those two potential outcomes for each individual, and then average, or the expected value on the distribution, we might want to sort of estimate this by just looking at what is the average salary of those with a college degree, and look at the average salary of those without a college degree, and subtract the two from each other. And this is somewhat what we call a naive estimator. It's a relatively simplistic way of looking at this effect. And in the next slides we will talk about where it goes wrong. But you can imagine that this is a logical next step to take. You look at the average salary across those with a college degree and the average salary those without a college degree, and you subtract the two. But it does assume that the level of the salary without a college degree would have been the same for those with a college degree, and the salary of those with a college degree would have been the same for those without it, right? So you are making strong assumptions about how these two groups, those with and without a college degree, do not differ on any ground other than having a college degree. So because we are talking about estimating the causal effect based on quantities that we cannot actually observe, so we cannot measure, can't measure the income somebody with a college degree would have had for if that person doesn't have a college degree, or what a person without a college degree would have earned when this person did have a college degree. Because we can't measure those, and we are still looking at the causal effect for that particular individual, or on average, that a college degree will have had. We are talking about counterfactuals. We are really talking about looking at the difference between quantities that we can observe and some quantities that we cannot observe. So we are talking about what would have happened had this person with a college degree not have had a college degree, or vice versa. And so this overall framework is sometimes called the potential outcomes framework, but it's also called the counterfactual model of causal inference. It's not the only model of causal inference. There is a wide-ranging philosophical literature on what a cause is and how we can assess this. But this is how most economists or quantitative political scientists these days think of causal effects. And an important implication is that causal effects as such are always estimated, not measured. You don't measure causality. Causality is an abstract theoretical notion. We can observe correlations, we can estimate causal effects based on correlations taking into account controls, but we can never measure causal effects. So in this slide, outlining what kind of bias we then obtain if we use this estimator, we use a bit of a shorthand just because the notation becomes far too complicated, far too long. So when we say E01, we mean the expected value of Y0, the potential salary without a degree, for those who do have a degree, where the treatment is 1. Or if we do E00, we have the potential outcome of salary without a degree for those who do not have a degree. So E00 and E11 we observe in the data. E01 and E10 are more hypothetical. We can't observe them, but we can theoretically certainly talk about them. So we can then look at what happens if we use E11 minus E00 as our estimator for the causal effect. That is the average salary with a degree for those who have a degree minus the average salary without a degree for those who do not have a degree. Because those are the two observed quantities. And we can subtract them and take that as our estimate of the effect of having a college degree. So this slide then decomposes that effect, seeing what happens in terms of bias. And one thing we need to take into account there to assess how much bias we obtain is how many people actually have a college degree. So we need to think a little bit about the population distribution of the treatment. So we add this one feature here, which is pi, which is just the proportion of people that have the treatment, that have a college degree. I will leave the actual computation of this equation, it's in a note. The mathematics are in the note that is uploaded to the website, so you can look there. We are not going to discuss that now. We just want to look at the equation that you get. So look at the equation that after the decomposition. On the left of the equation, we have what we are calculating as our estimator, E11 minus E00. The observed average salary with a degree for those with a degree minus the observed average salary without a degree for those without a degree. That is what we can calculate. On the right hand side we see what we are trying to estimate, the average treatment effect. This is what we are after, which is this expected value of delta. So the expected value of delta is the average treatment effect, and what is on the left is what we are calculating to estimate this. So everything to the right of this expected value of delta, all the rest of the equation is bias, is deviation, because we're trying to calculate the expected value of delta, and we're doing that by calculating this E11 minus E00. So everything to the right of that equation is the part that is biased, that is deviating from what we try to estimate. And we can roughly separate that in two parts. The first is E01 minus E00. This is the difference in salary without a college degree for those who have a college degree and those who do not have a college degree. And we call this selection bias. So this means that there might be bias in who gets a college degree and who doesn't. You could, for example, imagine that IQ would matter. If you have a higher IQ, you will probably be more likely to get a college degree. You will probably be more likely to perform well in your job and get a higher salary. So those who get the college degree and those who do not are not the same kind of group. Their expected value of a salary without a college degree is not the same. Those who get a degree because they have a higher IQ and then also get a higher salary, they would also have had a higher salary would they not have had a degree than those who do not have the degree. So this is a selection bias. It's a different kind of group. Same with work attitude. If you have a stronger work attitude, stronger appetite for work, you're more likely to get a college degree. You are also more likely to earn a higher salary, regardless of whether you have a college degree. So this is selection bias. The baseline income, the potential outcome without a college degree is not the same for the two groups. And the second one is a differential treatment effect bias, which is maybe some people are better able to leverage having a college degree If you are very good at presenting yourself, at say you are good at doing job interviews and good at writing your CV and so forth, you are the kind of person who, when you have a college degree, are better able to benefit from this, to communicate this, to negotiate harder and so forth. Whereas maybe people who do not have a college degree are also the kind of people who are less able to leverage having a college degree, like negotiate a new salary or apply for other jobs and so forth. So this is then the effect of having a college degree would also differ between those two groups. So the bias can be because of two things. There are differences between those people who have and who do not have college degrees that makes them more likely to have a college degree or not. That would also impact on their income. Or there are differences between those with and without college degree in the extent to which they are able to leverage having a college degree. So the effect of the college degree is different for the two groups. And both those components separately lead to bias, in the sense that the difference between the incomes between those with and those without a college degree is not going to be the same as the difference in potential salary outcomes on average between having a degree or not having a degree. So let's go back to this concept of confounding, which we discussed before. So we also talk of confounders. A confounder is a variable that has an impact on both the treatment and the outcome, and therefore creates selection bias or creates treatment bias. Right, so we go back to these biases that we had earlier. I mentioned IQ, I mentioned work attitude, I mentioned ability to present yourself, maybe you could think of negotiation skills and so forth. These will all impact on whether or not you have a degree, and they impact on whether or not you obtain a high salary. And so those are confounders. All of those are confounding variables. Here's an example more from politics. If we assume that political knowledge leads to higher turnout, people that are more knowledgeable about politics are more likely to turn out in elections, then we should certainly take into account confounders such as education and political interest that will impact both how much people learn and know about politics and also how likely they are to participate. So those are confounders. So a more mathematical way of saying this is saying that the expected value of y, the outcome given the treatment t, is not the same as the expected value of y given t and x. The expected value of the treatment, the propensity to get the treatment, the propensity score, depending on x, would be different from the propensity score not taking into account x. So if you have that combination of factors, then we are talking about a confounding factor. If only one of those two is true, then not necessarily, right? So if there's a factor that impacts on having the treatment, but not on the outcome, then it's not a confounder. If you have an effect that impacts on the outcome, but not on the treatment, then it's also not a confounder. Both of these conditions on this slide have to be true for it to be a confounding variable.